end and itself, of course. And there will be 5 sections. The first one will introduce the model, then we will see a reformulation of the model which stands for the Markovian division process. Then we will state the main result and try to explain it as best as we can. And afterwards, give an example of the main result, which is commodities. And we'll end it off with the section, here's a format mathematical section, which is called analysis of function. So the model is very canonical. And we have a finite set of states, K, and we have a Markov chain in discrete time, Xn over K, which has some prior P, and the transition rule, which is given by the stochastic matrix N. So from now on, N will be a unit of the model. Remember, is a stochastic matrix. And we will have a sender who is an agent which in every time period observes the realized state of the Markov chain. So he uses the Markov chain in real time. And when he observes each time the state of the Markov chain, he is instructed to send a signal from a finite set of signals. And we will assume that the set of signals has cardinality, which is at least as the cardinality of the state of the Markov chain, so that if he wants, he can fully disclose the state of the Markov chain.
A capital Xn is what?
It's the n step of the Markov chain, the random variable, which is the outcome of the n step. Yes. This is the realized variable. This is the random variable. Yes. So a signaling strategy of the sender is a sequence of stage strategies, which maps histories, that is path, state, and signal that he himself can, together with the current state that he observes, to probability distributions over the set of signals. This is a classic strategy. And we denote by capital sigma the space of all signal strategies. It's compact, convex, and we can discount.
So here the strategy K is K is
the state of the Markov chain.
The state of the Markov and S
are the signals.
The signals. So, okay. And okay.
What do you mean by convex? Is a finite set.
K is a finite set, yes, but the space we allow mixed strategies.
It's also it's a convex strategy.
No, it's not a convex strategy. The space of strategies is convex.
You don't have if you view it as a mixed strategy, right?
Yes. Yes, yes.
You don't have there a history of other players?
No. Just the states of the Markov chain and signals. So as always, we have a Kolmogorov extension theorem, which implies that each signaling strategy, together with the Markov chain, induces a unique probability measure on the states, which is the infinite histories along the game of both states of the Markov chain and the signals that are sent. And now we can define the sequence of posterior probabilities. This is a random sequence. Each element takes values in the space of the rifts. And under a signaling strategy sigma, the formula for the posterior assigned to states L is the probability that the nth step of the process is L, given the first n signals sent. This is important. It's the first few slides.
So this is the belief of the receiver.
Yes, the receiver will soon be introduced.
So this is supposed to be
yes, yes. But the notation, everything is take you up and see that you
Okay.
okay. Okay, so now what is the Markovian persuasion game? So we denote the game by capital gamma. It has a discount lambda and a belief from which we start P. And in every stage n, the following sequence of events takes place. So before we get to the end step, at the outset of the game, the sender commits to a signaling strategy. He makes this strategy public. And so both the sender and the receiver can compute the probability measure which comes from Kolmogorov's extension. So at stage n, the receiver starts stage n with a prior belief, which we denote by Qn. And we didn't define it yet, but at the first step, Q1 is just P. It is the point from which we start the game. Then the sender observes the value of the Markov chain. He sends his n signal, Sn. And now the receiver who knows sigma and who knows the laws of the Markov chain, its distribution, he can compute the posterior Pn based on the first n signals that he observes. And the sender knows this as well, of course. And now in the next step, the receiver takes an action which is based only on his posterior. Okay, he's stationary in his posteriors. And when he takes an action, the sender obtains a payoff which only depends on the posterior. The payoff is U, where U is a continuous function. And we do not specify the payoff of the receiver. The payoff of the receiver can be general, and this can be a non-zero sum game. But the sender observes the action of the receiver, and therefore the sender knows his stage payoffs. Okay.
What is Q?
So now we'll define Q. So after the nth step, the posterior probability of the receiver is Pn. Because it is a Markov chain, his beliefs for tomorrow's state will be Pn multiplied by n. This is the Markovian transition. And this we set to be, we set Qn plus 1 to be tomorrow's belief given to base posterior. So Q1 is the initial probability at stage 1, and Qn plus 1 is the initial probability at each subsequent stage. And what is the initial probability at each subsequent stage? Yesterday's posterior times n, the Markov matrix.
What's special here is that the receiver is not splitting, right?
Yes, is essentially a dummy player.
In principle, the sender could the strategy of the sender could depend on the actions of the receiver.
Yes, but not in this. In this, as I said, it's a very canonical model. The sender is in full control. When the sender sends a signal, he already knows his payoff. Because he knows the posterior and he knows the function u.
So that's the expected payoff. Right?
No. This Pn is a random variable. Okay. So the sender, when he sends his signals, he views Pn, the realization of Pn, and then his payoff will be u of Pn. I do not define the total payoff in the game. This is just the description of the path of the game.
Yes, but what I'm saying is that that's a limitation of maybe a limitation of the model that it cannot depend on the actions of the receiver.
Of course.
Why is that? Why does that make sense?
So we based our work on two other works that did the same model. It is not ours original model, and there is. I also get the literature, but it is very difficult even to analyze these things. So we will see. Hopefully, in time, I will convince you that it is a really difficult model as it is.
No.
This is the technical reason, but I have,
Yes.
but I have another reason. It happens to just this week I worked on a very similar model in finance, and the justification there is that the receiver is the market who determines the price of the fair,
Yes.
and the firm to give a signal to the market about its value. And he cares, the manager of the firm, let's say, cares about the belief of the market. Not only this period, the next period, and the other period. So
Yes.
Why do you need PN, or why can't you work with just human?
No, because Qn is the belief at the start of every stage, but the actual payoff it depends on the signals that are sent
Well,
through Pn.
If M is reversible, then you could get rid of Pn, that is would be a function of Qn. That is the airway.
Yes.
But the something deeper is that you assume that the payoff is obtained now rather than a minute from now, which is the next stage.
The payoffs are, I need to associate the payoff with the end stage. The payoff with the end stage is the payoff at the end of the end stage. After,
It doesn't model it. If you just waited 1 second, then you could put the payoff as a function of Q and then the
Yes. Yes, this is true.
Is that important that you have P and
Throughout the talk, we'll mostly be concerned with Pn. Qn is right now just for the explanation of the description of the game.
again, it's not connected.
Yes. Okay, so the total expected payoff of the sender under the signaling strategy is the discounted sum of payoffs. Okay, and the value of the game is premium over all signaling strategies. So this is the game. This is the goal of the sender, is to maximize, and thus he wants to find the best signaling strategy.
Any function will do.
Continuous. You can relate it to the upper semi-continuous. It's very technical. The reason are some theorems in convex analysis where the maximum is that it is upper semi-continuous.
This is mathematical, but
Yes.
this is a function of probability. We assume that the payoff is a function of the probability vector. And there aren't too many functions like that. It's not that any function.
You can assume that it is upper semi-continuous. So you can assume that there are
No, I mean,
steps.
what does it speak of when it's a function?
We didn't spend too much time on making the model, selling it to be realistic. Most of the intrigue cases from those previous works where already it was noticeable that there is a big mathematical challenge and very little can be said, and we try to add a little bit of maybe.
But I'm trying to say that there is no much cost in assuming that it is within a convex. Okay.
U is continuous. Just
Right,
like
I'm saying that assuming that it's convex / concave is not very costly in terms of application. Positive seems similar, and that's too right.
okay.
Can you go back?
Yes, of course. Here,
No, one ahead.
yes.
So it seems that no matter what is the strategy, the expected value is the same.
No,
Why not?
the strategy determines the distribution of the ends posterior.
Yes, but
It may have different distributions under different signaling strategies. For instance, if the strategy sigma reveals everything, excuse me, if the
give the
strategy,
same signal every time.
yes,
So you get your expectation.
yes,
Now you can split it by saying I give you one signal for the upper side and one for
Yes.
the lower.
yes,
Again, you get your expectation.
yes, but this was true. The payoff was linear in the posterior beliefs, but the payoff did not be linear. Yes, it's just some continuous function. Oh. So the two works of Eli and Reynoso and VA, they examine the same model, but for specific functions U, which come from economic interest, and for specific families of Markov chains.
And that function is concave, convex.
In the second work, the function U is it is a step function. It equals 1 on some domain in the simplex and 0 on the other domain of the simplex. And in Eli, it is something similar also.
So just to understand, there are utility function for them, it's better to be not informative, to send the same signal, right?
Yes.
And there are when you want the entropy to be the maximum.
Yes, the entire crux of the model is to understand the two primitives U and M. The function U, which is the payoff, and M the transitions, the relationships between them, they essentially determine what is the optimal use of information by the system. This is the main goal of the model, is to understand how this repeated the interaction affects the sender. This is always in repeated games. You want to maximize today, but it may have implications on the future. So, but U and M here are the two forces that the sender should.
In the previous words, the function was not moving.
Upper semi-continuous. And in our work, upper semi-continuity works as well.
So it's a generalization.
Yes, yes. And the first step to analyze the model is to reformulate it in terms of an MPP. So the MPP will now have a state space, which is not the state of the Markov chain, it will be the space of beliefs.
MPP stands for.
A Markov decision process. It is a stochastic game with a one player. And we will need to specify in this Markov decision process not only the state, but the actions, the transitions, and the payoffs. Let's begin with the actions. So assume that we have 3 states in the Markov chain, and we have 5 signals. And we look at the simplex, and we are at some belief Q. This is some belief in the simplex. So what is the action in the MPP? The action is to find the polytope with 5 vertices, take Q1, Q2, Q3, Q4, and Q5, such that Q is within the polytope, and to specify the coordinates alpha I of this point Q inside the polytope. Okay, so the action consists of 2 parts. First, tell me the boundaries of the polytope, and second, tell me the coordinates of the point with respect to those boundaries.
The Qs are fixed, they are part of the specification of the game.
We need to define in MPP the available actions at every state. The states are now the beliefs. So Q is some belief, it is a general belief in the sequence.
You have 5 Qs given, which are.
Yes. Yes.
What is Q1?
This is the action. I now define a new set of actions in the Markov decision process. The actions consist of give me 5 points corresponding to 5 signals, so that the point Q, the state, is bounded within those 5 points, and specify to me the coordinates with respect to those points which give you back Q. This P should be Q.
Outside the triangle, there's no Q.
Yes.
Inside there are Qs. So what are the Qs and what are the S's?
This comes from the specification of the model, which we saw before.
Okay.
Right now, don't concentrate on this specification. I define an actions just in terms of a geometric procedure, not in terms of the probabilistic signals and so on and so forth. The actions are an exercise in geometry. At any point, you can give me any polytope that you want with 5 vertices, and you need to specify to me the coordinates of the state, the point, with respect to those vertices. There may be 2 available sets of coordinates, but you need to give me a set of coordinates.
The QIs.
They are beliefs.
QI is part of the action.
Yes.
QI is the test beliefs.
No,
now it's a new story.
it's a new story. It's not the QIs from the description of the game.
So in this new story, what are the QIs?
They are beliefs. And at state Q, the actions available to the player are polytopes together with coordinates. The polytopes should have 5 vertices, QI, and the coordinates give you back Q, the point from which you started.
The action is splitting Q into 5.
Why do you call it speed?
No, this should be Q. This should be
Okay.
Yes, this is the point.
And the number 5, there are 5.
Yes.
So the action now in the new story is picking the 5 Qs.
Yes, and the coordinates.
And the code.
Yes. So why this is in fact
I'm sorry, the system is, you are part of specification of the game, they are.
no, those are actions. What are the actions in the MVP available at state Q? What actions can the player replacing the Markov decision problem can take? His actions are any set of 5 beliefs that you want. So the Q is bounded in the polytope, which is generated by those beliefs. And together with that, his action also consists of coordinates. His action is the points Qi, the vertices of the polytope, and coordinates which give you.
So the answer to my question is that the receiver chooses the QIs.
The sender.
The sender, you can choose any.
Yes.
Any QI.
Yes.
Okay, I thought this is the action. The action is taken by the receiver.
No, this is now a Markov decision process. It's a game of one player, and the player is
Okay,
the sender.
sender, okay.
Yes. But from here on forward, forget about the receiver. He did his part in the
Okay,
So we are talking about like Bayesian persuasion.
Yes.
You can take the belief and
yes.
believe it. Different beliefs.
Yes. Okay. So you got is everything clear?
Q is given and he chooses the QI
At any state,
and
yes.
returns the alphas.
No, we chooses the QIs together with the alphas.
Together with the alphas.
With the alphas, yes. So this is to all of you who were in the one paper in this topic to know the Aumann-Maschler splitting lemma. You can using signals and the lotteries which store in the states, you can get any such polytope that you want with the signals and so on and so forth. Okay, and of course the interpretation now from geometry back to the original story, the coordinates alpha I are also the probabilities of sending the signal Si, and the QIs are the posteriors on K given the signal Si. This is just a translation back to the language that we some of the coordinates. Egal is everything. Okay. And now the mathematical notation for the action. So at any state Q at the MVP, the set of splits scripted S of Q is the pairs of beliefs and coordinates so that they sum up back to state Q.
Yes, I will put this slide for the.
Okay.
The other one. It's a good idea to define.
Okay, I will
So
do
there
this.
Previous slide, what did we learn? That you can describe it nicely graphically.
Geometrical. You can think of the exercise of the sender in this game purely in terms of geometry. Because later in the talk we will
But only in of dimension 3.
no, in any dimension.
Okay.
Only it's difficult to
Okay, okay.
yes. And now the transition rule. So given that the state is Q and he chooses this action, what will be tomorrow's state? Tomorrow's state will be QIN with probability alpha I. This is what we saw at the beginning in the description of the game. With probability alpha I, the posterior becomes QI, and then tomorrow's state will be QI shifted by N. This is the transition rule of the MD. So it's a stochastic transition rule. It depends on probabilistically on the values of the alpha R's.
Previously, you had PI multiplied by N. Here we have.
No, I had QI multiplied by N there as well. I think, unless it was typo. Let's see. Yes, here we have the N. Okay, but now we don't talk about the sequential. We only know the MQ. I just describe the transitions in the MQ. So these are stationary transitions at every state Q. If you take this action, the posterior becomes QI with probability alpha I, and then the tomorrow state, the new state of the MQ would be QI times N.
Can you identify PI?
PI
PN.
is QI.
PN is
Yes.
the
PN,
random variable in which with probability alpha I,
Yes.
the value is QI,
Yes.
that's clear?
Yes.
No.
No?
Yes.
What was Q should be Pn, then Qi was.
No. Q is the initial belief at every state in the description,
Which was Pn.
which was Qn. Qn is the initial belief at stage n. Then, if the outcome of the split is Qi, then Pn is equal to Qi. The posterior becomes Qi. And the initial state tomorrow will be Qi, which is in our terms the posterior times n.
What about the utility?
The utility is just the expected utility with respect to the split. With probability alpha I, the payoff will be Qi. So Qi are the posteriors. This is exactly like in the description of the model. The payoff depends on the posteriors.
So this is the payoff. So if you go back to the original model, this will be the expected.
This is in the description of the MVP, we specify payoffs in part, not in expectation. Yes, the expectation will be when we take the gain sequential, Q itself becomes a random variable, right? It is the initial belief at stage n and +1 and +2. This itself will be random, and then we can take expectation over everything.
So,
This is just in the MVP for state and action. What is the number which is the payoff? This is the number which is the payoff. And let's take the very degenerate case where the discount in the MVP is 0. So this is the one-shot game. So the goal of the center is just to maximize with respect to all splits his target payoff with respect to those splits. And this is a very famous problem. This is the classical Markovian persuasion model by Jens America. And the solution to such a problem is done via the quantification method. So for each function u on the simplex, we introduce scar to be the smallest concave function, which is at least as big as u, at least as small as u. So here you see an expression for the car. And the theorem, which comes originally from our Mathler, is that for any belief P, V0, the optimal solution to the Markovian persuasion problem is W at P. So this is the one-shot game. So in the one-shot game, the best that the center can do at this belief here is to guarantee this. Okay?
I don't remember, I made the assumption that I have enough signals for this.
And you need at least this number of signals and the number of states in the Markov chain.
So that's
Can.
already true here.
Can.
Okay.
Yes, excuse me. We assumed it already in the start, the signal
Yes,
set.
yes, but I was wondering why this.
Yes.
So, okay.
So what is the actual action is in terms of the terminology used before. So by Theodorov's theorem, there are always k points, so that the cap can be represented as a convex sum of u at those points. And then the center will just choose the polytope, which consists of the points pi's and the coordinates alpha. So in this case, if this P, the polytope which the center chooses is P1 and P2, and the coordinates here are uniquely determined by the point P. Those are the coordinates which give you back P. Okay, so this is the exercise of the center in the one-shot. And now, when lambda is not degenerate, when we have horizon in the game, so we, as in any MVP, we have a Bellman equation. So in the Bellman equation, it gives us a formula for the discounted value. At any belief P, any initial belief P, the discounted value is the supremum over all possible actions, which are now splits, of today's payoff, discounted by minus lambda, plus the future payoff discounted by lambda, where the states in the future move according to the transition rule of the MVP. This is the dynamic programming principle for our MD
These are all splits of what?
of P. We start with P. P is Q1. It is the
Previously, this was a split of Q, and here you split P.
yes. P is now the initial belief. It is a primitive of the model. The primitives of the model are U, M, the discount factor lambda, and the belief from which the game starts P. Okay.
Why in both it starts, I starts by one
Where?
in the brackets.
Here,
I and the other I. From two, no?
the set of signals.
This is the signal.
Yes,
Not about the future. Okay.
yes,
B lambda is all.
yes.
Like as the eagle, I wonder why you use P at all, not Q, because you have Q1, but you want this equation also on the other stages, not just.
So then the dynamic principle, the dynamic programming principle gives you this formula only in terms of what happens today and everything else in the future. There is no release, but
I was just about notation. You have Q.
what is Q?
What is Q? What is the
They
belief
have P.
on day N? How do you denote the belief in day N?
The posterior or the prior day n.
The prior.
The prior day n is denoted by Qn.
Okay, so why do you need P at all? I don't get it.
Because the payoff is determined by Pn. The payoff in our game, let's see. The payoff in our game is determined by the posterior stage n Pn. Okay. So as said before, if U was linear, I'm right. As I said, if U was linear, then it's the same to look at the posterior, the prior, because the expectation of the split is the same as the initial belief. But when U is general, then it's sensitive, of course, this change.
Before you go to the
Yes.
infinite sum, if you took two periods, let's say the weights were half
Yes,
between the periods.
yes.
Then you only take the average of the two graphs and take the quantification of the average.
So this will be a lower bound than what the sender can achieve, if I understand correctly. But what is the best that we can do? Maybe
Isn't it the best? It's the
I-
best.
no,
No, each period, if,
not necessarily.
okay, then
What you mean is take the curve
Then
of the average.
did you think about, because I don't want to waste the time now, but did you think about the model of instead of taking discount, taking the average? And
So-
then the result looks to me intuitively very simple, but
We will see that our results in the paper are simple. We take lambda to go to 1. And
then it's
then,
like taking the way.
yes, it's like taking the Chesser law to go to the.
Isn't it to take the steady state and take the average of the
No, we will see, we will see. Not, I mean, maybe in some cases it is, but in what we do, it is, okay. So a very nice application of Carter-Theodoris theorem is that this supremum over splits essentially guarantees you the curve of a different function. What function now? The function which is 1 minus lambda times the base pay of u. Because notice that here we split both u and both v lambda concatenated with phi, where phi is just the shift operator. So from now on, every time we say shift, treat it like we multiply by m the value. Okay, phi is the shift.
Okay, this one to part the correct.
Yes. Okay, so curve of what? Here 1 minus lambda u. This is the function, and here the function is lambda times v lambda, where inside you shift by n.
So it's function of the all
This is the
for this QI.
yes.
We have the D lambda. D lambda of yeah, okay, you do the shift operator, then you multiply P lambda, multiply by lambda. And then you want, okay. Is the implication obvious? Yeah, this is just
what is the best splitting? It is the cup. But now the split is not only of U S
You
Q,
take the
but it's
alpha I out of the expression. Take it out. Okay.
yes, they
Alpha I is some
this
function of
is
Qi.
our
So it is a function of Qi if you
and this is a very nice expression, I think, because it is a Bellman equation which is purely in terms of functions. There are no longer splits here. It is written in a very compact form, but unfortunately, even in this compact form, it is very difficult to solve it. So Eli, in his original paper, solved this Bellman equation for a specific Q and a specific M. This was the contribution, and even the solution there, which is a two states and simple functions and transitions, is very turned out to be very difficult. And two corollaries of Theodoros theorem of this formula is that for each discount, the function v lambda is concave on the simplex, because it is the cover of something.
the function B lambda is
On the simplex, it is an integral. And the second corollary, which is more deep, is that for any lambda and for any belief, the value of the Markovian persuasion game is the same for all signal sets which have cardinality at least k, the cardinality of the Markov chain. This is Theodoros theorem. The best split is always achieved with the number of states and the dimension of the simplex. But no, the dimension of the simplex is itself -1 in our case. Okay, so this is a nice corollary from this. That starting from the k plus first, k plus second signal, the sender gains no benefit. He only needs to concentrate on what he can do with k signals. So this is nice. You got questions?
So the cardinality of the set S is
It's like the simplex k. The simplex is on k.
right. Is it clear from this expression, not from the motivating question, that there is a solution here? Well, obviously there is a solution to the question that you posed.
The solution is because when U is upper semi-continuous, you maximize over a convex and compact set. The splits, the set of splits is convex and compact. And here we have U upper semi-continuous. V lambda is concave, is also achieves the maximum on this convex compact. So the supremum is attained.
Here the condition is that the cardinality of S is greater than K.
Yes.
And in the next slide, you say something about the cardinality.
Yes, we can concentrate only on the case where the cardinality is exactly k.
No, I'm still
Yes.
want to make.
Yes.
Okay, so it's this operator. You plug in one V lambda, you get it on the right hand side.
Yes.
You get another V lambda.
Before this, let's agree why here, why the maximum, why the supremum over all
Yeah,
strategies.
this explanation I can understand.
The maximum here is attained.
Yeah,
Yes.
I'm just wondering whether it's clear from
Yes.
this equation that this operator has a fixed point. That you have there is some V lambda when you plug it in the right hand side to get it back on the left.
So I think that continuity and compactness. So it's vital to use the risk. What is written here? Well, this gives you the optimal action at every state of the entity.
As an operator over functions,
Yes,
you have the space, the
yes,
state function
yes.
of the feedback.
yes, the curve is a non-expanding operator on the simplex. With respect to the infinity norm, curve of f minus curve of f minus curve of g is at most f minus g in the infinity norm on functions. The curve is always non-expansive. Yes,
Okay. But does it guarantee the existence of fixed point?
I think.
To be sure, the
Functions can be like linear functions.
On the C,
Can go like this.
with respect to the non-expensive operator, you have here, say, d lambda is the parameter of the non-expensive operator, right?
Yeah.
And so you have here d lambda equals to this operator. And now the question is whether this entire thing is non-expensive. So I think that if you will write it on paper and using the fact that the curve is non-expensive, with respect to everything, you will get the whole operator itself is non-expensive.
But that isn't sufficient to assure a fixed point. You don't need it to be.
I don't know, I think so, but I'm not sure 100% of
I
them.
think maybe because you take the average of two functions, V lambda appears only on one part, maybe it's even more than non-expensive, maybe it's evolution.
Contracted.
Yes, because the lambda is strictly between 0 and 1.
Maybe it's
Yes.
contracting and then.
Yes, yes, it's 1 1. Yes.
Then you get. It's complete.
Yes,
So in the graph that you show of the example with two peaks,
yes,
right? So if I get to P2,
yes.
it's better for me to be non-informative forever.
No,
Why not?
this is exactly the Markovian. You end stage 1, say with the spin, you end stage 1 at P1. This is the realized posterior.
That's a P2.
P2,
Just to be sure.
P2.
Okay.
Tomorrow's state will be P2 times n.
Right.
P2 times n can lie anywhere. So if P2 times n lies, say here, if this is P2 times n, what should you do? You can split back to P1 and P2. But if P2 times n lies, say here, okay, so it depends on the M sheet. This is his
So the next period is not, it's not.
the same. The M sheet moves it around.
So in not, but on average, the receiver will be in P2, right?
Yes, but you will start next stage, it's P2 times n.
Right, but on average from now on, it will be P2.
It will be on average P2 times n, and then in the next stage, P2 times n squared, we will get this. We will get this.
Okay, this makes sense.
Okay, so what is the main reason?
Even construct, it's something true, because it's just plugging something like that.
So what is the main here? Right now, the notation will not be clear. Evgeny, how am I with time?
20 minutes.
20 minutes.
Or
Okay.
it will be like.
No, I hope that in 20 minutes I can please tell the main result. So the first item in the characterization is that for every epsilon, there exists a delta sufficient to be big, such that V lambda for lambdas greater than this delta is close to the optimal solution of the one-shot problem at the stationary distribution of the Markov chain up to epsilon for every belief. So what is the first type? Let's see it in a more vivid way. So we have here the theorem states that there exists an asymptotic value, always there exists an asymptotic value, which is at most the optimal solution of the one-shot problem at the stationary distribution, such that V lambda converges uniformly on the simplex as lambda goes to 1. So as the players become more and more patient, the values converge to some number. Okay. So when you are patient, essentially you don't care from where you start. And this is very natural because in ergodic Markov chains, you converge to the stationary distribution. So if you are patient, you can wait until you are close to the stationary distribution and then act essentially from the stationary distribution. So the first theory result here is that there exists an asymptotic value. And our theorem tries to characterize when does it achieve its upper bound. When does this upper value equals to W at the stationary distribution. What it means more stochastically, it means what are the cases in which the repetition of the game has no effect on the sender. When is this stochastic environment has no effect? This is exactly the case when the sender, even in a very long game, can guarantee close to the optimum of the one shot. Yes, a priori, yes. A good demo. You need a priori. Yes, because you need that P times n to the power n converges to pi. In the proofs. If it is just irreducible, you have the averages converge to pi, but not the powers. So you need for the proofs that the powers converge to pi. Okay.
Statement I is the first, is the previous one.
Yes, but I try to say what this is the main result. What do we try to characterize in the main result? So I right now try to explain item 1. What we try to characterize is what are the cases in which a very patient sender can overcome all of this stochastic story with Markov chain and everything, and guarantee close to what it could do if it would to play a one-shot based on persuasion.
You say these are equivalent statements.
Yes.
And I thought in the previous slide that he said that statement 1 is true.
No. In the previous slide, I said that an asymptotic value always exists.
Oh, now you characterize the.
Yes, I characterize when does this asymptotic value achieves its upper bound. Now, view of pi. And for the proof, if it is just irreducible, I don't know to say that the asymptotic value is constant. It may depend on the initial belief. In the way we prove it, maybe there is another.
It shouldn't, because just wait, you can wait long enough, and also take a randomization on the time, the waiting time, and then you get the same thing.
So maybe I cannot decisively tell you that it is correct or incorrect. I don't know. The proofs go very smoothly under the ergodicity assumptions, which is both irreducible and the upper level. Maybe it can be extended to just reduce.
You don't really have to know much about B lambda. You just say if I'm patient enough, then starting playing from day 1 or from day 100, I get the same.
Yes.
And from day 100, I always start with.
No, but from day 100, the belief is not always stationary distributed, not always
This is when it's period. If it is period, then instead of waiting until time 100, I wait to the random time between 100 and 105. Then I always do.
I think that it will work. Okay. And okay, so what we try just together.
Statement 1 is that V infinity equals power.
Yes.
So why don't we-
No, yes, less than the curve.
No,
No,
this is,
Technion one.
yeah, this is the characterization. Where does it equal, when does it equal the cup? So there are two conditions which right now cannot be interpreted.
why don't you write? You know,
This is, this is more sort of, this is more economic writing than mathematical writing. If you want to implement, the first statement is P infinity equals to the cup.
let's say that.
Yes.
Don't try to confuse my.
So the second and third condition of the characterization, we need to specify several things. We say that there exists some Z in capital lambda. What is capital lambda? Such that AZ, what is AZ? Contains an M-absorbing set. What is an M-absorbing set? So we now need to explain everything to make this all clear. So let's start with M-absorbing sets. I'm not
The first is part of the result was what Alan suggested. That if you patient enough, then the value is the.
but just of today, Alan said you take the average over times and
Take into account the dynamics of the beliefs. Just at the same point.
of pi m is the solution to the one-shot problem with no continuation after the first stage. Okay,
You say that if I'm patient enough, then the value of the game, no matter what is initially is, it's the codification of the function u at the station.
yes, under some conditions, it's not always the case. It is the case only if those conditions hold. And now we will go to those conditions.
Okay, so what I'm suggesting, the equivalent there exists.
Yes, now I will need to specify everything.
And M absorbing.
Yes, it is not defined yet.
Now there is no.
It's a great problem. We solve it.
NZ. Okay, so this is something that I don't understand.
We will now define everything.
Okay, there are some conditions 2 and 3.
Yes.
which are equivalent to saying.
Yes. Yes.
Well, be happy about what you've done. Nobody is happy.
No, I just didn't read.
It's not even done.
So what is an M-absorbing set? So let's take some set of beliefs in the simplex, and we will say that it is M-absorbing if its shift of any point in the set lies within the convex boundaries of the set. Okay, so for every point in the set, when you shift it by M, you cannot get out from the convex boundaries of the set. So to give some motivation to this example, let us think about it as an exercise in a soccer. So our field, the set C, is the union of the circle and the triangle. Okay, and now the exercise in soccer is that you start from some point Q and you need to pass the ball to Qn, and then you need to pass the ball to Qn squared, and you follow this passing mechanism. So this set is M-absorbing because the passing mechanism.
How did you get out of the sequence?
No, this is not a sequence. This is some triangle in the sequence. It's not a sequence. So this set is M-absorbing because the ball, the triangle, union with the circle. So this set is M-absorbing because even though the ball will leave the set itself, it will not leave the convex boundaries of the set. The convex boundaries are the green set. Okay.
If you start in the set, you always end up in its convex.
Can we see that?
Is it equivalent to saying that the convex part of the set is the environment?
Yes. So yes. So a set, if a set is M-absorbing, also its convex hull is M-absorbing. This is linearity of the condition, the matrices and so on. Also, if the set is closed and convex, then its set of extremal points, which spans the set itself, will also be M-absorbing. This is prime Ehud. So this is the examples to an absorbing set. So the first example, if the set is an absorbing, its convex sum is an absorbing. This is linear. Prime Riemann implies that if you want to take the external points of a closed convex and absorbing set, it will also be an absorbing. And the last property, base property, is that the union of an absorbing sets is again an absorbing. This follows from some inclusion, a simple inclusion context.
And M absorbing implies the convergence. When you take the power to,
The power of the set.
no, the power of M. Of the method, of the multiple.
And
No,
then
in your graph, it was like convergence. Your graph, it is the.
what here we talk about set of beliefs, not point. It's not a single point, it's a set of
Right,
beliefs.
if you start with some belief in this M observing set.
Under the ergodicity,
Multiplied by M.
under the ergodicity, any point of the simplex, any point in the simplex, if you multiply it by n sufficiently,
Convergence.
it converges. Here we talk about something that happens
On the way, it doesn't get that.
yes.
Oh, the convergence point is in this. Object.
On, I see that you
Is
have,
under the term,
we invented it.
yeah,
Question.
I would call it invariance, but it's not exactly invariant.
Yes.
It's the context of the context. It's a set of context. How is it like?
So let's give examples. So let us assume first that the stationary distribution pi is this point. So this point is replicated in all of the simplexes. So the stationary distribution itself is clearly in M absorbing. Return to it. Also, the external points of the simplex itself are M absorbing, because everything from the simplex returns to the simplex itself. Any goal with respect to the L2 norm centered around the stationary distribution is M absorbing. And this is also true for the L infinity goal. Everything for Rod, everything follows from the fact that the operator norm in these two norms is close one. And in the L1 goals, they are M absorbing when N is double stochastic. Okay, so these are examples of M absorbing sets. And this is, of course, not surprising that pi, the stationary distribution, is included in all of those sets somehow. Because by Brouwer's fixed point theorem, we must have that pi is always in the closure of the convex hull of any absorbing set. Okay. So absorbing sets are clearly include pi in the weak sense, is in the closure of the convex hull. So now we know what is an M absorbing set. Now we need to understand what is capital lambda and what is AC. So now we return back to convex analysis. So for each point Z in the k-dimensional space, we introduce a linear functional parameterized by Z, Fc. So what is Fc? It has a pre-term which is kappa u at the stationary distribution, together with the inner product of this parameter Z with x minus phi. X is the input of the function of the linear functional, and Z is the parameter of the linear function. So what is important about this defined function that when we plug here pi, this cancels out, and we just remain with kappa u of phi n. So all of this family of linear functionals across all Z gets to kappa u at phi at the point phi. This is immediate from the definition. And now we only want to look at Z. So now we think of Z as linear functionals or as hyperplanes in our case. We now look only at those hyperplanes which are at least as kappa u on the entire sequence.
Oh, wait a minute. The first term was.
Yes. And here we have linear leads.
Oh, it's not you.
Now I function.
Often.
Yes. Okay, so we look at all the hyperplanes, which are at least as kappa u on the entire sequence. And because all of these points, see all of those hyperplanes at phi agree with kappa u of phi n, then this set lambda is exactly all the hyperplanes that support the graph of curve U at phi. Those all the hyperplanes which are above curve U and touch curve U at phi. You can and the notation so far, okay? So the set AC is now among all those supporting hyperplanes. I look at those beliefs Q, where the function U, the payoff is equals to the linear function of it. So what do we get to make order the notation? We know that the hyperplane of U is at least as curve U. It's U. This is because the other plane supports from above.
So this is the linear part of the curve, something like that.
Yes, yes. And U is below the curve. So any point here, any belief here is a belief where U agrees with the curve. So in this example, here is that there is a single supporting hyperplane at phi n. Here is curve U at phi n. This is the supporting hyperplane. And now we look at those points where U touches the supporting hyperplane. So these are P1 and P2. Those are the points where U touches the supporting hyperplane. Okay, so what is AZ is beliefs. Those are P1 and P2. Those are the beliefs where U touches. Z is some parameter which gives you this hyperplane. I didn't write U explicitly. There is a single supporting hyperplane in this example. To curve U at phi n. At this point of the graph of curve U, there is a single supporting hyperplane, this hyperplane. But in more than 2 dimensions, things can go crazy. Okay, so for instance, if we
You might have many supporting hyperplane and Z is the normal. So for some Z there is no supporting. It might be an empty set. AZ can be empty.
no, AZ always exists by Karl Theodoris, but we initially constrain ourselves only to those Zs, where the defined function is above the curve. It is always a non-empty set because the graph of curve is a convex set, can always be supported. But based on if it is differentiable at the point or not, there may be several supporting hyperplanes.
These are all
So I don't see why AZ really depends on Z.
Yes, we will see later. Or let me give you an example in advance, because I don't think we will get to it. Here, for instance, if this is W of phi m here, this is the function W of phi m. There may be 2 supporting hyperplanes. This supporting hyperplane and this supporting hyperplane. Okay. So the set AC can consist of the points where the first supporting hyperplane intersects U, this point, this point, this point, and this point, and also points where the second hyperplane intersects U. So this is also this point. So AC can be the union. Okay, so for every Z can be
So there are different ways to split the point by M and get the
yes.
set.
These are all sub-differentials.
Yes. This is exactly the super gradient of the yes. Okay, let's refer. Okay, so I just want to point to that already in 3 dimensions, the set AZ can be a pretty general set. There may be many points where the supporting hyperplane touches U. On this point, you see it is a peak here of the mountain, and here it is a sort of a lower peak, and so on. So
Any supporting plane, the union over the supporting line.
okay. So 2 important properties of the curve. First of all, is that within the set AZ, within its convex boundaries, the curve will always be an affine function. It will agree with the supporting hyperplane. You can see it here. Between those points, either convex half, the curve is just linear. And this is true in any dimension. Within this region where U intersects the hyperplane, inside it is always agrees with the hyperplane. So the concavification operator for general knowledge, it is either the function itself or it is linear locally. Okay, and the second use.
Belongs to the contents of AZ?
Yes, because AZ itself is here 2 points,
Right.
but it is linear in their context out in the entire segment.
So in general,
Yes,
the curve is either linear or
the function itself, yes. Locally, it may have different linear pieces, but okay. So this is useful.
If it's linear, what do you say, right? If it's linear,
Yes,
the
but
strategy doesn't matter.
but no, it does matter because it's not linear everywhere. It can be linear
Yeah,
somewhere.
if it keeps staying in the linear path.
Yes, you keep saying correct.
So the strategy doesn't matter.
Exactly, exactly. So I will already smell in advance the main result. And just the second important property of the curve, which for general knowledge is if you take some weights and some beliefs that average to pi, if the average of the function of those beliefs is the curve, then each of those beliefs must be on this hyperplane AC. Okay, you cannot get the curve using the split if the split is not exactly those extremal points where you touch as
For some,
yes. So what is now the main result? The main result is as follows. A patient sender can guarantee close to curve U if and only if the set AC contains a set which is n absorbing, which always goes inside. So what is before the mathematics? What is going on here?
in the state.
Yes, but I want to explain it. It will be easier this way. Here the set AZ is P1 and P2. What it means that it is n absorbing, it means that phi 2m and phi 1m go inside the interval
It's always.
where it is linear. But we want to guarantee value of phi m in the next stage. So what is important? So a very important property that plays part in the proof is what we call a mean consistency property at phi m. This property starts with the fact that the posteriors satisfy a probabilistic identity, which is very close to the martingale condition. The conditional expectation of each posterior given last day's posterior is last day's posterior shifted by n. Because in the next day we split Pn times n. This is what sometimes is referred to as an n martingale. This is the probabilistic structure of the posteriors. If we take expectation and use the law of expectation, we get that the expectation of the n plus first posterior is the initial belief P times n shifts. And this will be true for any sigma, for any signaling strategy. So if we start from the stationary distribution, the expectation of each posterior at every day will be exactly the stationary distribution itself. Because when we shift the stationary, we remain at stationary. So what do we infer from this? That each posterior Pn is itself a split of the stationary distribution, but Pn can now be supported on the number of signals to the power n. Because you take the tree, you split, and so on, but still the mean will always remain the stationary distribution. So at every day, no matter which strategy you use, you will end up with a split of the stationary distribution. And now by Jensen's inequality, you will get.
What does it mean for distribution of the split of the distribution?
Again?
Pn is distribution.
Yes.
And the split of the state of invariance.
Yes.
What does it mean for distribution with the split of
What does it mean for distribution
to be a split?
It is a mean preserving spread.
The
is a distribution over next pair of belief, which is a split of,
Yes, the shift.
yeah.
Okay, so by Jensen, the expectation of U at any day is at most curve U at the expectation of the belief itself, which is the stationary distribution. So let's summarize. According to the asymptotic law, a patient center can wait until it converges essentially to the stationary distribution. And then he faces the problem with the prior, which is the stationary distribution. By the mean consistency property, at any day, he remains with the same expected posterior. So he cannot guarantee more than curve view of the stationary distribution on any day. So how can he guarantee across all durations the curve view? He needs to guarantee it every day. And now, in the absorbing, because the mean is still high, if you could make the posterior at any day is still supported either on P1 or P2, its expectation will be exactly the stationary distribution. So the goal of the sender is to make its posteriors supported on P1 and P2 on any day. Okay, this is what he wants to do to guarantee the couple of.
I didn't figure out what you're doing because I missed the slide with the two conditions.
So I think the condition, yes,
Explaining, but I think they tried to prove it. But I don't know what.
the statement is that in this example, a patient center can guarantee curve of 5M. He can guarantee this if and only if the set P1 and P2 is M absorbing. Why? Because if it is M absorbing, the beliefs return back to this interval, and then you can split each of those beliefs back to P1 and P2. And repeat this exercise at any stage. You move inside and then you split back out.
And you said that you can never get more than half of
You are fighting. Yes.
this is what the other.
Jensen and the mean consistency. Yes. So the theorem, right now I'm trying to convince you why it is a sufficient condition. Each time that we move inside, we guarantee the curve. Less obvious is why it is also necessary. Why, whenever a belief moves outside of this P1, P2, you cannot not guarantee the curve again. Okay, so this is the theorem. Let's now, with this demonstration in mind, let's now read it again. A patient center can guarantee close to the static optimum. It can override the stochastic environment and the repeated nature of the game and so on, if and only if there exists some supporting hyperplane. So that the points in which this hyperplane touches you contains a set which goes inside.
So you show that you can never get more than half of light.
Yes.
This is generally true. Now you can really get this number if there exists a supporting
Hyperplane.
plane that contains an absorbing set.
Yes. Now the set can be a subset. Let's see. For instance, in this example, AZ is the green ones, but the absorbing set can be just the 3 points. But the same exercise can be repeated because you first split pi to those 3 points, and then you enter back inside the blue triangle, and you split back to the vertices of this triangle. So this is the sufficiency. If there exists an absorbing set, it is sufficient for the curve. It is also necessary. This is less obvious, and this is the characterization. This is the only case where the center can override the stochastic environment, if this condition holds. If it doesn't hold, we cannot guarantee the cover view at pi n. So, 2 open problems. Okay.
M absorption does not depend on the strategy.
No, M absorption is only dependent on the structure of the AZ. AZ only depends on U, on the function, not on the structure.
Not on you.
Yes, so notice in the theorem that there is the theorem uncovers one aspect, possibly there are several, on how the interrelationships of U and M play. The set AZ comes strictly from the geometry of U. How does the supporting hyperplanes touch U and its cap and so on? This is just U. AZ is strictly in terms of U. And the M absorbing set is strictly in terms of M. So this gives a joint condition on U and the M. Whenever this condition is satisfied, we can say something about the behavior of the player in the game.
Okay, and now you haven't told us what is the countable.
Yes, this is one can prove in the paper that any M absorbing set contains a countable M absorbing set. It is a
So if you
exercise.
say countable out, the theorem is still correct.
No, this is for every,
Yes, for
well,
every, yes,
So my question is, if you take out countable, the theorem is still correct.
what do we mean take out?
Or do you still want countable?
Yes,
The theorem is still correct.
yes.
So why don't you do it?
This is just, if you read the paper, I think that you will understand why we not do it. Right now, the paper has a slightly different structure of propositions.
If you took the
It's
most
like-
countable, then one suspects that you take it out.
no, it's like 3 is strong and 2 is weak.
Yes.
Right?
But it's still the same whole.
Because it says for every and count.
Yes.
Now I don't see the something. You said that, well, from the pictures. I
Yes.
couldn't follow
Yes.
look at the picture, so I think pi m is always in the convex hull of AZ.
Correct.
Okay.
Correct.
Pi m, so if you just take pi m, 1 point.
No, but phi m is not itself in AZ, it's in the convex hull. If you want phi m might be below
Oh,
the cup of U.
so you want the subset not of the convex hull of AZ, but the subset of
AZ is stricter, yes,
which is, and that set has to be.
M absorbing, yes.
And
So, okay, so, AZ. Now you say that AZ. Need not be absorbing. Because. Yeah, because pi can just throw it on. And then.
And control you out.
Yeah, so you can get out of the.
Hyperplane essentially, fall below the hyperplane.
But, you know,
And then you cannot recover. This is
and
what,
then you say that instead of there exists supporting hyperplane, you say it's equivalent to saying that it's true for any.
yes.
For any hyperplane and not only that.
No, for any supported hyperplane, there may be several supported hyperplanes. As we saw with the roof. This is the point and this is the point. So each of them should contain an absorber.